No camera.
Awesome they are.
No camera. Hello. There we go. Yay. All right. Chalk Talk will start in just a moment. I'm just gonna get. The light's not too bad here, actually. Huge problem. Yeah. Pretty huge speculator, but at least on that, this moment,
So we have like all these modular rigs, like whereas in Voodoo we put everything in one rig. And here it's 3 rigs. One rig for actually it's 2 in Voodoo and 3 here. One separate rig just to wrap. Because it's just so big. So is it okay? Can we do so we can cash it off to the extremes and like that? And maybe to that. Exactly. Yeah. So just stuff like that. It's all. Yeah. It's a little frustrating. I don't know if you know, funny enough to
it's a moon.
Actually, do you know what it is?
It's a wing and person.
Okay. Okay. Hardcore. That's great. That's awesome. Listen to the I'll pick them up. Yeah. Okay.
But there's no light to the camera itself.
Right.
Is there? Oh.
Okay.
How would you pay him to have this conversation in my earshot?
He does that for free. No, he's. I mean, he's convincing me to talk to you guys. Or everybody cares really confident. I'm not putting any weight in this call.
Oh, there you go.
Yeah, totally on drink time.
Oh,
yeah,
nice.
Yeah. Dream about some machine learning. Learn what you guys are up to.
Well, actually, we're not. This is going to be very, very low level autoencoder kind of stuff. Because we're not going to get. Fortunately, the use because I'm gonna do something absolutely horrible here. Is zoom in this camera and try to parallax. And I'll try to write in big.
Only write big over there. Get smaller as you come.
Yeah, exactly.
Oh no.
Clean the lens.
Yeah, definitely need some focus.
Okay, here we go.
I'll try to fix it as you go along.
Yeah, we have top people working on this. There we go. It's coming into focus. There we go.
Right.
All right. Today, this was a request by people wanting to do this as well. This is something that's really exciting. So first of all, a little history about this. We've already talked about autoencoders, and we are so going to just talk about them again. We're going to start right from the basics of autoencoders. this variational autoencoder, if you read machine language stuff, or I mean machine learning stuff, there is a huge push for generative adversarial nets or networks. These guys are all over, and they're producing some unbelievably cool results. And every time you read them, they all, in the same breath, mention that this is something that is very tightly related to it. And variational autoencoders are actually a simpler way of doing what generative adversarial nets are doing. And the key word here is generative. What we want to do is be able to put together some machine learning stuff where we train something so that it has the ability not to sort of recreate or figure out what was going on when you gave it something, but actually create stuff from whole cloth. We want to be able to, given these neural networks that it hasn't seen before, and it kind of like imagines. So classic case for this is faking pictures. You give a generative adversarial net or a variational autoencoder a whole bunch of pictures of celebrities, and you train it with that. And eventually you get this thing so it knows what celebrities look like, and then you can ask it to give me a picture of a celebrity that I haven't seen. Not a specific person, but just something that looks like a celebrity. And these things will actually do that. That's variational autoencoders will do it in a simpler form, and often they're a little bit fuzzier, but they still look pretty good. So that's what we want to do. We want to train a machine learning thing with something so that it basically understands what that space, that area of thing that you're training it with, so that then you can ask it later, hey, give me this back again. Give me something that you are just sort of imagining exists. But before that, we're going to start really, really, really basic. And there's a great thing on deeplearning.net encoders. And they're actually fairly simple. And especially if you haven't heard of this, these two words, like variational autoencoders, what the hell do they mean? So we're going to start out with autoencoders themselves. Autoencoders all by themselves. And it's actually pretty simple. Oh, wait, we're getting some steps to walk. All right. So let's think about neural nets and give you a full-blown example. Say we have a picture, and I'm going to take this picture. It's a picture of a person or a cat or whatever. Let's put a cat here. I'm going to build a neural net that takes this thing. So we'll put this into our neural net. I'm going to make a big box here for our neural net. Oh, how'd you do that? You turned on a light.
Yeah, where's the switch for this?
Where was that?
I think you plugged it in.
Oh, I have to learn. That'll help, right? Yay! System rules. Awesome.
Thank you.
Look at me. Wait. We're gonna. Hold on, we're gonna do one last thing because the motor on this bad boy does not.
Oh, right. Yeah, I forgot.
But that's okay. We're just gonna point it. Yeah, that looks way better. All right, we're feeling good now. All right, so we're going to take this thing. We're going to put this in a neural net. Or all this stuff is neural nets. There's a big black box that's a neural net. And we want, I'm trying to draw this correctly. We want the same image to come out. And that's what this autoencoder is. It's a thing that says, look at images, and I'm going to figure out basically how to encode these images. And so you take the input to your neural net is something that you're feeding it, And you want the neural net, when it works on the input, to do stuff to it. There's all sorts of machinations going on inside here. And at the end, we want the exact same image to come out. And you're going, why? Because we're going to go into some of the details of it. But for now, just take it as read that this would be useful. That if you took an image, stuck it through the autoencoder, and you got the exact same thing on the output, that this would be a cool thing to have. All right. So how does this work? And then we'll explain why this is cool along the way. Neural nets. First of all, you have layers in the neural nets. And the first layer is an input layer. So I'm going to draw this as just a whole bunch of pixels, and I'm going to go all the way down here. And if this is a 100 by 100 image, well, let's do this easier so it's easier. I don't have to draw as much. A 10 by 10 image of a kitten. Then I have here, and I'm just going to take the pixels of this image and stretch it out. So I'm going to put this pixel here, and this pixel here, this pixel here, and so on. So this sucker is called the input layer. Right? And on the exact same thing over the same input layer, and it's got the same thing. We're trying to produce a 10 by 10 image here. So we have here, this pixel goes here. And just for ease of use, this is a black and white image, and the values in this pixel go from 0 to 1. And this is a black and white image, and the values of this pixel, the pixel goes from 0 to 1. So far, so good. And then what I'm going to do is create two parts of it. There's going to be a thing that takes this and encodes it into a value. So we're going to call this value y. And the way we're going to do this is with all those connections, right? You're going to have, whenever you see a neural net, you have all these connections where you have a bazillion, all the way down to there. And how many of these are here? Well, that's going to be that. But each one of these guys has access to every single one here. So the way we do this, and associated with each one of these lines is a weight. We're going to call that alpha. And this will be an alpha that goes from pixel 0 to y0. So we'll call that 0, 0. Goes from pixel 1 to y0. So this one is alpha 1, 0. And so on. So this is alpha 2, 0. And this one, this guy kind of drew it here. So this one would be alpha 0 to 3. So 0 or 2. So there'd be a whole slew of weighting on each one of these lines. And then also associate offset of B0, of B1, of B2. And I'm going to draw that off to the side because this is part of the math. The y value, the y0 here, y1, and y2 are what's going to be calculated by all these things. And I'm going to write down a piece of math that makes this make sense, hopefully. Yeah.
Yes, when you're doing these autoencoders, is it typical to use a fully connected, or is it, do people use convolutional networks?
Ooh, okay. So what
No idea.
Joe asked an excellent question, and the question is this basically what these things look like? And it's an awesome question in that this black box that I have here really has an input and an output, but the black box is going to be very different depending on what you want the autoencoder to do. So what I'm doing right now is the most basic of all possible autoencoders. It's got one hidden layer, and it's going to have two sets of weights: the weights that connect the input to the hidden layer, and the weights that connect the output to the hidden layer to the output. So with this, we get some very basic possibilities of what this autoencoder can do. layers in here. If we have layers that have more than one hidden layer, because we can do that, we can put a whole bunch of these Ys in here. Then what we can do is start capturing more and more nonlinearity. We can capture some really interesting behavior about the stuff that we're trying to encode. And you have mentioned convolutional autoencoders. Indeed, especially when you're looking at using fully connected layers where everything can see the same. Convolutional layers, which are connected by a filter of shared pixels, those show up a lot when you're dealing with images. So this is, again, part of the art of machine learning, is saying, all right, I understand the concept of autoencoder. How do I get it to work for my particular thing? And then the one other thing about this is once you've started building this, how many layers I have and how all this works, how many values do I store there? And I'm going to put that off to a moment, because this is the core of autoencoding. Because that question mark is going to come back. We're going to come back to that sucker. And actually, I love this. This drawing was going to go, but it's getting confusing to me, so I want to do this. Y here. This is Y. That's Y0, Y1, Y2, and that kind of thing. And all these guys are connected here, and there's a beta associated with that thing. And then there's also a function, an F, that we're going to pass this value through to get to Y. And so let's put a connection here, an F here to go to there, and an F here to go to there. So in order to clear this up, let's look at a little bit of math. Compute the value of Y. It's actually pretty easy. I'm going to take A, or alpha, a whole bunch of alphas, and I'm going to go alpha 0, 0 times x0 plus alpha 0 times x1 plus alpha 2 times x2. You're getting it. All the way input. I've multiplied each and every one of the input values by the weights, added them all up, and then 0. And then I put it through a function, F. Or actually, sorry for doing this, I was doing F because it's function, but the paper uses S. So I'm going to stick with the paper, or the website that I'm using uses S. And this nonlinear function, well, it can be a nonlinear function. This is the nonlinear function that takes this value, which can be a big value, and maps it to a value between 0 and 1. So we've talked about this before whenever we've done this. This could be a sigmoid function, or the tanh function, or ReLU. Doesn't necessarily have to be from 0 to 1, but it just basically maps it all the way through. So sigmoid looks like this. Tanh looks just like it, except centered at 0. ReLU looks like this, where it's 0, 0, 0, and then boing, goes like that. So what this basically says is compute a value, figure out where it lands in this function, and then return the value that it lands. So if the value is huge, this is assuming we're going to use sigmoid here. If the value is really negative, and if it's how you build it, about -3 to +3, it returns a value on this slope. So it basically compresses this so that it goes down, and you get a value in here between 0 and 1. And it's neatly differentiable, but it is not linear. Non-linear aspect of this. So think about what just happened. This whole image, stretched it out, and then we created weights that we multiplied on each one of the pixels of this thing, and then put it through this little function. So we took, I love thinking about this in terms of, And these weights, which can be arbitrary, we're going to be talking about how to get those in a moment. But we're looking at the whole image and we're condensing it down into a single number. And we can do anything to that image with these weights to create that single number. And then we do it again. We take the whole image with a whole other set of weights and condense it down into another single number. And so on. We end up with, well, how many alpha values do we get? We have for each pixel, or there's an alpha per input. 100 Ys times 100 per output. Numbers that we use 10,000 alphas that I need to figure out a value for. 100 because I only have 100 offsets that I add, and these functions are exactly the same the entire way. So the function does not change. It's a sigmoid or a tangent or an RLU. So this is a way of looking at the entire image, doing something, basically transforming the image so that it now has a single value representation. Then we do it again. We do the exact same thing for the output. All this, guys. And we have a whole nother set of alphas. Alpha, 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 and there's beta, or B0, B, D, B, and then there's another S in here. So we do the exact same thing. So think about what we've just done. We've taken the image, done something to it, encoded it into this new representation. And then after we've taken this new representation, we basically said, okay, but I still want an image. So I'm going to decode that representation into that image representation. And then we do something so that we expand it out or do something to it so that we get an image back. All right, that's where the encoding comes into place. We take the input, encode it, and then we decode it to get the image back. How do we build this thing? Well, you have to initialize some value. And typically what you're doing is you initialize your alpha values to pretty much a random number that's Gaussianly distributed around 0. Because we'll probably get negatives and positives, but you pretty much use a random number generator to implement values to something that has a nice distribution, but crazy random numbers, but they just all start out around that. You don't set them all to 0 because that would break this thing. You set them to some number. With the betas, or the Bs, you typically do set the offsets initially to 0. Them to random. You can actually set those guys to 0. The function itself, that's defined. That's part of how you're building your thing. The one thing is whenever you're using a toolkit to do this, you basically get to choose this function. You say, I want to hit when you're building. These things are called activation. The tool building. Right there, and I want to use activation. This is the act. My grad student go through the number. When we were doing images of kittens. And we run this through there. Single, and you know, the I equals 0, first image, and we let it, it's random initialized numbers, kitten gets stretched out. An encoding of the kitten into the outside, nothing. It looks totally random and how to compare these two. And this is where we build a, right? We say, this thing produce what we gave it. How well did it do? Now, of course, it won't. It'll look like crap. It's going to look like a whole random jumble of pixels. All right, how far away is this from what I want? I'm going to compute this loss function. I'm going to basically say, this isn't right. You know, how far away I am. That, and use that back propagation thing that I've talked about before, where I look at changed in this image in order to make it look more like my original image. Take that, the change that you need in order to make the loss function, and you start propagating it backwards, and you change the betas and you change the alphas, gives you new y's, and then you change the betas and you change the alphas. You do it again. Because now our alphas are ever so slightly better at producing that first kitten image. New image, and we go to I equals 1 now. It through. And the second time we send it through, it's going to look like crap. It's still going to look like crap because we only slightly adjusted this. But it might look just ever so slightly less like crap. Again, we look, how far away was I from this kitten now? Back propagation, where we swoosh it back and change all the B's and the alphas to make it look a little bit better. And show what happens. You get 100 or 9,050 a kitten through here, and it's going to really start looking like a kitten out there. Now, the big question that should be floating in your mind right now is, doesn't this just converge images? Just build 1 1 1 1 1 0 0 0 0 0. So there, or whatever, maybe it's not 1 1 1 1, but 1 and a whole bunch of zeros, and the next one would be 1 and a whole bunch of zeros, so that you just pass this guy right through to y, and then you pass this guy right through to y. This paper even says this. This nice little description of this, and they say, if there's no constraint besides minimizing the reconstruction error, one might expect an autoencoder with n inputs and an encoding dimension to learn the identity function. Why wouldn't you? Wouldn't it just do that? Surprisingly, because of the way this thing is being trained, it never ever happens. What it's actually doing is looking at the statistics of these images. All these images live in this sort of image space. These apart what makes this thing a kitten picture. This is really powerful. It rarely ever converges to I, and in fact, I would expect that it would never ever do that. As long as you use, what you're going to do is build something that has an understanding of what this kitten space is. We're going to talk a lot in the variation. So now,
Teacher out of bug.
and this, it really is. He says, surprisingly, experiments reported in book in 2007 when trained with a stochastic gradient descent, which is what we're doing. Autoencoders, which is what we've got in your parts, with more hidden units than, as long as y is greater than inputs, yield useful representations. It means that taking the encoding as input has a low classification error. That's really, really cool.
So you want this to be more higher dimension?
Well, no, this is just, wow, you just went to right where I was going to go. So what Joe just asked was, wait a sec. Here I have a great big question mark, or a little bit of a question mark right there. How many values are here? Now, first of all, well, if I have 100 inputs here and I have 100 inputs there, it could be an identity matrix. But what if instead of 100, this was 25? And this is where I wanted to talk about kitten space a little bit. Kitten space.
Patent pending.
Exactly. I have, if you think about this vector, I have a dimensional space of all possible images. Draw that. So I'm just going to draw a three-dimensional thing. One dimension, and this is going to be 0. This will be pixel 1. It goes to 1 and 0. So there's cube here, right? On this thing is a cube, represents all possible images. Every possible image that you could form can be represented by somewhere in this cube. And this is exactly 3 pixels. But if I have 100, I've got this 100-dimensional thing, but it's still this 100-dimensional cube. So every possible 3-pixel combination can be found in here, right? Black and gray and black. Then I'd have that pixel right here is black, and gray would be 1, right there, and then black would be down there. So a black-gray pixel would end up right there, because that's a little hint. So let's start thinking about this. This is a 100-dimensional space, and we have 3 pixels. Kitten pictures. There's always going to have, there's locality to kitten pictures, because you're going to have the center of the picture, you'll have some background. The background may vary. The color of the kitten is going to be different. Start seeing that they're going to start clustering. You'll have kittens over here that'll have a variety of possibilities. And then you'll have kittens over here, and then calico kittens, and kittens with their off to the side on the image over here. And all of a sudden you start looking at this, and of course, all possible pixel or images sparsely populated by kitten pictures. And the idea is that this thing is actually going to have a shape. And again, 3-dimensional, but this is and it's still going to have this shape to it, right? Basically describe that if I'm inside this, and the shape may be disconnected, it might have some weirdness, there might be all sorts of craziness about this. There's this sort of, if I'm inside the shape, I have a fairly high probability, and that's the first time I've said the word probability in this lecture. Very high probability that if I chose inside that shape, I'd actually produce a kitten. Over here, I've got an incredibly low possibility of producing a kitten. I've sort of wandered out of kitten space. I'm closer to the shape, and the shape is sort of irregularly formed. All of a sudden, I've got a fairly high probability of creating a kitten. So what have I done with this autoencoder? I have started taking this, and I've said, okay, and transform it into some hidden layer here. Hidden layer, work with that. And if you think about this, I need in order to describe this shape. Well, one thing I need is a 10,000 kittens. So I could have 10,000 kittens and I'd have all these points. In terms of a general probability distribution, a sort of minimum that I need to describe this shape. But this is very sparse. This is not filling this entire space here, especially when you think about it in 100 dimensions. Maybe I could use a lot less information, come up with some way of encoding where I am in this. When I'm at one of those encoded locations, I've got a high probability of creating a kitten. See where I'm going? This is kind of cool. You've got this weird ass shape here, code into how many? Well, right off the bat, especially if this was an identity matrix, I can prove to you that if I have 100 and 100 values in my thing, I can prove by, just sort of, if all this stuff was identity, I could exactly describe that shape, because any picture that I stuck in here, same picture out there. But it's a crap description of it, because what I've basically done is described all. What I want to do is force this thing to interesting description of this kitten space. And one of the ways of doing that is shrinking the number of values. Say if I do this 10 here, I want you to describe this kitten space values that I'm encoding. A 100 by 100, or a 100 dimensional space to encode all this stuff. I'm only going to use a 10 dimensional space to encode this. Cool. And that is a form of compression. So this, one way of thinking about is that it is a way of compressing. I've taken this kitten space, and if things work out correctly, I've trained my system so that it into 10 values. Values here, because I know I'm looking at kittens, that I can take 10 values and expand it out like this. This is not a non-lossy compression. Of course, and what you're doing is starting to talk more about probabilities that we're going to create the right image. So that I can take this kitten image, throw it here into 10 values, and then expand those 10 values back out. Extraordinarily like the kitten image that I've gotten. I'm going to stop for questions, because this I feel questions.
No. Oh, no.
Oh, no.
I always slow you down when I ask questions.
But you've got a question.
Is there any reason mathematically you would expect the compression thing to converge to like a principal components as opposed to?
He asked the right question.
As opposed to just some random.
You asked a perfect. Did you read ahead?
Makes you expect that there'll be a useful or a optimal set.
Well, first of all, I'm going to stop right off the thing. Where's read the right thing. Because this actually, in a certain case, sorry, just a moment. They actually mentioned this. Right. The hope is that the code Y is a distributed representation that captures the coordinates along the main factors of the variation in the data, which is kitten space. That's what I just said. This is similar to the way the projection in principal component analysis, main factors in variation in the data. So you're absolutely right. And in fact, your hidden layer, so if there's just one hidden layer, hidden layer so that my activation unit is not a point function, but it's actually just a line. There. And the mean squared error criterion, the loss function that I'm looking at is just looking at how is the mean squared error of how this image compares to the other one. The K hidden units learn to project the input in the span of the first K principal components. You can build an autoencoder, start training it with these things, will eventually converge onto a principal component analysis. The exact same results by taking all your images, big matrix, doing principal component analysis on that image, and you get the exact same, this thing will produce the exact same result.
And you're saying they can prove that? I mean, not asking to run through proof, or
yes.
Maybe you will.
Yes, I believe they actually can prove this. I do not have a reference for you though, but you know these guys have been doing a lot of math on this kind of stuff. Okay, we do not. Analysis are very much a linear kind of thing. You're looking at this, it's a linear algebra thing, where you're looking at a matrix and how it multiplies onto a vector. Because we have activation units that are nonlinear, and because we can have multiple hidden layers. Way more than just principal component analysis. This basically draws this sort of, you know, convex hull of stuff that it can capture. For weird-ass shapes in a really interesting way. So this is a superset of principal component analysis. In fact, you really have to crush this down in order to get to principal component analysis.
Is there a general heuristic, like a general rule on the ratio of the scales of this input vector to your, so that you get better training times or better results? I mean, if you make that 1, it'll be crap. You're not gonna get anything. If you make it,
Can you? Yeah, that's If you make this input value 1 value between 0 and 1, you're not gonna get that. Yeah, it's like looking at the first principal component of a thing.
Do you know if there's a general rule that you talk about?
Well, there's a well, I think again, this is where the magic or the sort of art form of building up neural nets are. But first of all, let's talk about this. Well, maybe we'll get into variational component. This actually works out well because we've laid a good foundation for where variational component, the variational aspect of this is. Okay. Let's talk about what we do. So a typical thing that will happen is that I'm going to stop drawing the connections, but I'm just going to start drawing inputs. Hidden layers like this, I could add 2 hidden layers, right? I could have hidden layer 1. Compress this down into something, maybe there's, and then maybe this is, well, 30 as well. It doesn't reduce the amount of expressivity of what I've got, linearity to it. I think that's the key thing. Hidden layers, hidden is kind of correlated with linearity. So if you expect this shape to be completely bonkers, where you're getting a whole bunch of variety in there, compress that. With just one hidden layer, you've got a certain amount of nonlinearity. You have this matrix times this one function, and you've got that. More hidden layers, I'm going to be able to capture kitten spaces.
You use then the last hidden layer for your kitten space, and then if you're going to do inference later, you're going to say, here's a new set of values. You're just going to plug it into the last layer to generate your output.
Well,
right?
Well, okay.
Sorry.
Nope. That is exactly that. Excellent question that I didn't answer right now is why are we doing this again? So I have a thing that goes in here and compresses and stuff like that. Thing about this. Before we get to the variational aspect of this, this is the other talk that we talked about is rather than variational, we could do denoising. So what this thing is doing a way of representing this kitten space. And I can start training this thing. And this is one of the cool things about this. It doesn't converge to an identity matrix. Basically analyzing this kitten space and coming up with a representation of this shape in this here. So what I can do is with kittens, but then after a while, I could start saying, you know, with kittens, where some of the pixels are missing, I will replace the pixels with salt and pepper values, or I'll replace the pixels with black. Send this through. I'm still part of the training session. And so what I'm basically doing is saying, you know, this space that I've got used to be nice and smooth, but now I've got values that are sort of falling out of it. I've got a kitten space where I've got some pixels that are not quite in the kitten space. And what you're basically doing is hoping that you can pull those guys back into kittens. So what you do is you take a picture of a kitten, corrupt it, you compare what you get out of here to the uncorrupted kitten. 30 black pixels in this kitten. See what I get and compare it with the perfectly perfect. That's pretty cool, right?
And how does that? Like, so you compare it,
right? You compare it, and then you know the first time I do this, I might actually get a picture of kitten splotches on it.
Yeah.
So now I'm going to put a delta in there.
Yeah.
It's going to push that back and say, no, no, no. It needs to be pushed back into this probability space. Even though I got a value, this is the probability space. This is right.
The pristine image that you're using as the output or as the target, messing it up on the input. So,
and I guess the thing to think about is this is kitten space down here, and I'll just draw it in 2 dimensions here. And
you're saying
right.
that's part of the training set.
Exactly. The training set might have values, and let's plot this here. And I'm gonna cut to the chase in here. I might have encoded values that fall around this nice normal distribution here. I know how to go from encoded values into kitten space. That's what my weights and everything do. If I have an encoded value that when I went through here, produced a value that was outside of this encoded value, so that it actually produces a value back inside kitten space. A value that might start because it had some black pixels in it. But I'm going to train this thing to nudge that encoded value back into the normal distribution. This thing begins to understand that even though I'm getting values of kittens, I'm producing values of kittens on the output that look good. Let's go in. Good kittens go out. In fact, these kind of autoencoders have been in use for quite some time. Audio processing. You will have just pure on audio autoencoders that will clean up telephone conversations. They're running in the background of a lot of things where they've been trained on a lot of voices. They know what voices sound like. So they know that when you get static, sound more like a voice. Remember, this thing isn't trained on, it's trained on kittens. So when I get a kitten with black spots on them, make kittens that look that cool. You're basically pushing this thing back into the area that you want it.
In that case, you're going to train it not, but on
Noisy image out.
original image out,
Right,
and it would only be trained.
Yeah. Another cool thing about this that is another paper I was reading about this in the most basic way. They said, and this was actually for autoencoders. They had a sine wave, and they corrupted it with noise. They put noise around here. And they built, in this case, a recurrent neural network, but it works the same way. I've read lots of papers mention this. If I train that with this kind of data, and yet I feed it that looks like this thing would be well, actually. It's really good at pushing things back into that probability space of the original sine wave. You've added extra noise. It has the same kind of qualities, it just is a larger magnitude. It's actually pretty good. It's back into this original shape, even though it's never seen noise like that. Very cool. 6 minutes, and I'm going to just stop right here because I'm going to go back to that word compression. In here, what I'm going to do is go back to my original thing. We're going to do this in two stages. And next week, not only are we going to autoencoders, but we're actually going to run some examples of this. I'm going to bring the computer up, and we'll have some examples in Tiano and Lasagna. How this works, it is fun. We have 0 to 10 hidden layer Y has 10 values. If I stop here, this part, let's draw it in red, here is encoded, right? Here decodes the data. All right. So one thing I could do right off the bat to make this useful is if I took a picture of a kitten here and stop. And all of a sudden, if I just have this autoencoder thing, I've had a way of taking a kitten picture and compressing it by a factor of 10, a relatively decent result on it. This compressor for a specific kind of image. So if that's the case, wouldn't it be cool attached sliders to this? Slider in Maya to that value, attached a slider to Maya and this value. So there's a slider and there's a slider. And I started sliding these values around. I actually took them by hand and I went, and this. I'm kind of exploring kitten space. I have this weird ass 100-dimensional space that I've come up with in an encoding of. I slide these values down. Produce a kitten every time I move the slider. And the answer is no. It turns out the answer is no, unless you do something fancy. What you have to do is tune this. You want a basic autoencoder, and all it is basically a way of compressing or data. But the variational aspect of it says, okay, tweak. What we're going to do is take this value right here, and we're going to add a constraint to it. We're going to say that this constraint makes this normally distributed, and I kind of drew it there. I kind of jumped ahead of myself there. Normally distributed around this. We're going to constrain what the values are possible here. But the key thing with variational autoencoders is that the training becomes a little bit different, because now not only are we training this, we're comparing how well did we create a kitten, how well did we create a kitten, and how good is the encoding is the constraint that I built. And that constraint, the values that you're producing here, values in kitten space. You're basically forcing it into kitten space. You're
aren't you going the other way around? Aren't you changing what kitten space is from some sort of little blobs that you're expanding it so that it fully occupies the hypercube?
Oh, that's even a better way of saying it. Oh, yeah, that's a great way. I don't know if it's the right way, but I think that might be the right way. Yeah. Right. Because now, any value that you have between here, because it's normally distributed,
You're changing.
but the hypercube of this space now isn't,
It's not. There's no emptiness. There's no.
there produces a kitten. Wow. Now we're gonna talk about this because there's the way you do this requires a little bit of math, and that's where probability is going to come up even more. Is that we can start once we've done this, we take this part away, right? Is these 10 values, these 10 sliders, and we can move around and we can say, please generate me a kitten that I have never seen before, but I know that it's in kitten space.
What kind of training do you need?
Same. It's the same.
But how many images are you training? Like, what kind of number of images do you have to fully flush out that space? It's only you must need a massive amount of variation.
Right. I drew, when I was drawing those dots in there, you don't want this thing to be two very distant dots. You want to make sure that as it's flowing between there's a kitten. It's starting to really statistically analyze the space. The example we'll do next week is on the minced data set where we train it with images of digits. Values back and forth, we're going to get digits coming out of there. And they are typically training with 50,000, and it works pretty damn well. 50,000 images looks good. I don't know how many you need for kittens. Kittens is
more than 10 kittens.
Yeah, but it's we can get to that data. All right. Now, one last thing I'll do. If you just look and Google for variational autoencoders TensorFlow, or put whatever neural network package, PyTorch, Cafe, throw it out there. You never have to write any of this stuff. This stuff, you just download it and you can start throwing dogs at it or pickles or whatever you want. You can make your own for blobs of images that you have. And it's actually pretty easy to use, so doing that. And in fact, that's what I'm going to do. I have a couple of things that I've been playing around with in Lasagna. Layer on top of piano. And we're going to go over how to do it next time. Probability and the math that goes into this. This good. Do you have an intuition of kitten space now? Bye, everybody. We're going to get kicked out, and I'm surprised we haven't.
At GTC, Greg Heinrich give a talk on this.